Can you hear me? Yeah. Okay, so thank you very much for the invitation to speak here. It's always a pleasure to come back to Tel Aviv, and I am particularly grateful for the opportunity to have great hummus for breakfast. That's the top from my point of view. So we will continue with the topic of scattering amplitudes, but from quite a different perspective. So here I will not discuss any perturbative expansion where I separate tree-level from loop contributions. I will just discuss the full scattering amplitude and its non-perturbative amplitudes. So this is work done in collaboration with Miguel Paulos, John Toledo, Balt Van Ries, and Pedro Vieira, who is here. And how does this work? So the motivation for this work is very clear. Basically, our goal is to extend the success that we had in the recent years in the conformal bootstrap to massive quantum field theories. Okay? So here we want to apply the bootstrap philosophy, where we don't try to solve any specific or any particular theory, but we just analyze the general set of consistency conditions to bound the space of all possible theories. Okay? So, of course, this idea of the S-matrix bootstrap was very popular in the 60s, and in some sense, it gave birth to string theory. But we really think that now it's a good time to revisit the topic in light of what we have learned with the conformal bootstrap. So we think we can have new things to say about this old idea. So the first part of my talk will be about setting up the S-matrix bootstrap in two-dimensional quantum field theory. Then I'll generalize to higher dimensions. And then I'll briefly explain how to connect this S-matrix bootstrap with the standard conformal bootstrap. And then I'll finish with some open questions. So let's do S-matrix bootstrap in 2 dimensions. So I will consider the 2-to-2 scattering amplitude. So in 2 dimensions, there's no scattering amplitude. So by 2 dimensions, I mean 1 plus 1. So the S-matrix is just a function of the energy, or if you want, the Mandelstam variable S. I'm considering scattering amplitudes of, say, the lightest particle in the theory, which has mass m. And what do we know about this scattering amplitude? Well, we know crossing symmetry. So this is a function of S, but equally is a function of T, which is just 4m squared minus S. So there's some reflection symmetry. And we also know analytic properties that just follow from the spectrum of the theory. So here, during most of my talk, I will consider this spectrum. So I will consider that I'm scattering a particle of mass m, and I will allow for a bound state, or if you want, another stable particle of mass mb, and then I'll have a continuum starting at the 2-particle threshold 2m. Okay? So that implies this analytic structure for the S-matrix. So this is S, Mandelstam S complex plane. So I have a cut associated with the 2-particle continuum, and I have the cut in the T channel, so the given by this reflection symmetry, by crossing symmetry. And then I have poles associated with this stable particle. Okay? So this would be the S-channel pole at S equals mb squared, and this is the T-channel pole. And in principle, I could also have a pole associated with the particle m itself, appearing as an internal particle. But for simplicity, I'm forbidding that. You can think that I have a Z2 symmetry that forbids the cubic coupling between the lightest particle. Okay, so these 2 properties we already know. The final property that we know about the S-matrix comes from unitarity. Sorry, before saying that, let me just explain. So here, in this pole, the residue is what is my definition of the cubic coupling, okay? If you want the non-perturbative definition of the cubic coupling between the external particles and this particle of mass mb. And now we have unitarity. So unitarity is just a statement that the modulus square of this scattering amplitude is a probability of going from the two-particle state to the same two-particle state, and that probability has to be less or equal to 1 when we compute this amplitude just above the cut, okay? So for physical energies bigger than 4m squared. Okay? So these are the properties we know about this S matrix. And now we're going to ask a bootstrap type question. So the question I want to ask is, for the given spectrum we chose, what is the maximum value of this cubic coupling? Okay? So what is the biggest residue that this S matrix can have? So physically, we expect this to be a finite value because you should think that this cubic coupling generates an attractive Yukawa potential between the particles. So if the cubic coupling is very large, this attractive potential will form more bound states, which we are excluding by assumption. Okay? So if we fix this spectrum, then we expect this cubic coupling to have a maximum value. But okay, this is just a physical argument. Actually, the problem is very well posed. You need to find a function with these properties whose residue is the maximum possible. So this is a very well-defined problem that has an analytic solution. Okay? So the analytic solution is given here. And let me just explain you some simple properties about this analytic solution. So it's obviously crossing symmetric. And you can see that it has a pole at s equals mb squared. And the other crucial property about this solution is that if you calculate it for s bigger than 4m squared, this is a pure phase. Okay? So the modulus is exactly equal to 1, which means that there's no particle production. Okay? So the probability from going from two particles to two particles is exactly 1. So there's no room for particle production. And this kind of formula, it's a combination that appears often in the integrability literature. So it's called a CDD factor, and let me define this notation. So this MB is the parameter and it's a function of S. Okay? So the proof that this is the optimal solution is actually very simple. So let me just tell you the argument. So define the ratio of the S matrix we're looking for by this explicit CDD factor. Okay? So now this ratio function is completely analytic in the plane minus the cuts because the poles cancel in the ratio. And because this CDD factor is a pure phase on the cuts, then the ratio is also bounded by 1. The modulus of the ratio is also bounded by 1 at all boundaries. Okay? So you have an analytic function in some domain whose modulus is bounded by 1 in all the boundaries. So that means the modulus is bounded by 1 everywhere. In particular, it's bounded by 1 at mb squared, at s equals mb squared, but the ratio at mb squared is just the ratio of the residues. So it's just our cubic coupling divided by the residue of this explicit function, and that's bounded by 1. Okay? So that's actually the bound that we derive for the cubic coupling just follows from this. And so we can plot this bound, and it has this kind of shape. So as we vary the mass of the bound state, the maximum value of the cubic coupling is plotted here in this curve. So all physical theories that exist must live below this curve, and there's no physical theory that has a cubic coupling bigger than that. So what's remarkable is that there's actually a physical theory that saturates the bound. Okay? At least, well, just for mass of this bound state bigger than square root 2. And that's just the Sine-Gordon S matrix. So it's an integrable theory, so there's no particle production. And so it's the scattering of the lightest breather in the Sine-Gordon as exactly this simple S matrix. Okay? So this is a bound which is actually saturated. Okay, so this idea generalizes to many other cases. Here I'm just illustrating. So for example, you can have studied the problem with 3 stable particles instead of just 1. And depending on the values of the masses, you find different combinations of these CDD factors. But the point is that whatever the spectrum of stable particles you choose, the optimal solution is always a product of CDD factors. So it means there's never particle production. So if there is a theory that saturates this optimal bound, should be an integrable theory because it doesn't have any particle production. So in this case, for some specific values of the masses, for example, here we find that the 2D Ising model deformed by a magnetic field, which is an integrable massive theory, saturates our bound. Okay? That's just one example of this case. Okay, so this was the analytic solution, but this analytic solution does not generalize. We don't know how to generalize to higher dimensions. So what we're going to do is to solve this problem numerically, and then this method will generalize to higher dimensions. Okay? So the numerical approach is very simple. Basically, what we have to do is the trick that we do is to map the S-plane minus this cut to the unit disk. Okay? There's some explicit formula, but it's not needed. The point is just that we map the full complex plane minus the cut to the unit disk. And now, since we are in this unit disk, we have a very natural ansatz to write for the S matrix. So what we do is that we write the S matrix with an explicit part, which are the poles, in the S and the T channel poles, and then plus something which is completely analytic in this plane minus the cut, which is the same as saying it's completely analytic inside the disk, in these rho S variables. But then if it's completely analytic inside this disk, it has a convergent Taylor expansion around 0. Okay? So then we use that to write this ansatz for the S matrix. And it's also useful to impose crossing to think of the S matrix first as some extension where you have two independent variables S and T, and then you just put these coefficients symmetric so that crossing symmetry is automatic. And then when we want to calculate the actual physical S matrix, we just evaluate this in the surface S plus T equals 4m squared. So this ansatz makes crossing and analyticity automatic. So the only thing we have to impose is unitarity. So unitarity is what we saw before. We just calculate the modulus square above the cut. So we have this ansatz with these constraints. Now to make it viable numerically, we have truncate to a finite number of variables and a finite number of constraints. But that's very simple. So what we do, we truncate this sum to a finite number of terms. So we have a finite number of variables, this coupling and the coefficient C. And this infinite number of unitarity constraints, we also truncate. We choose some grid in S between 4m squared and infinity. And so we have a finite number of constraints. Okay? So now we just have finite number of variables, finite number of constraints. It's just a simple maximization problem to maximize this coupling subject to all of these, if you want, M constraints. And actually, this can be done even in Mathematica. Find maximum works very easily for this problem. And we converge to the analytic solution very quickly as you increase Nmax. Nmax doesn't have to be big at all. 5 or between 5 and 10, you already see convergence very, very well. Okay, so this is the numerical approach, and this is what we are going to use to analyze the S-matrix bootstrap problem, the analogous problem in higher dimensions. So okay, what's different in higher dimensions? So here we focus on the T matrix, and so we write a similar ansatz, now with 3 variables, S, T, and U. So again, we are assuming the same type of scattering of neutral scalar particles of mass m and only one pole. So we have the poles in the S, T, and U channel. And now we have this Taylor expansion in the row variables, which again map the S-plane to the unit disk. Okay, so this makes crossing symmetry and analyticity explicitly. So in fact, it makes the Mandelstam analyticity explicitly. It makes the biggest form of analytics, of expected analyticity explicit. So here we are assuming that because since we are constructing explicitly an ansatz, we can assume that, and if we find a cubic coupling, the maximum value of the cubic coupling we will find, is definitely a value that is possible, okay? Because we are just assuming analyticity, the maximum analyticity. So again, now we have to impose unitarity. So in higher dimensions, the most efficient way to impose unitarity is to decompose into partial waves. So we just take this t, we evaluate it in the physical surface, so when t and u are given by this s and x is related to the scattering angle, we integrate against the appropriate Gegenbauer polynomials, and we get the partial amplitudes. So these partial amplitudes now satisfy exactly the same unitarity condition, but now for each value of the angular momentum. So if you want, it's like scattering in the angular momentum basis. So as before, we just have to make this a finite problem. So again, we truncate this sum to a finite number of terms, to a finite number of variables, and we also discretize this S variables to some grid and introduce some maximum value for the spin. Okay? So again, this is a quadratic problem, can be solved efficiently using STPB. So let me show you the results. So this is the maximum cubic coupling for a four-dimensional quantum field theory. So the plot has a similar shape, but here let me just emphasize the difference in convergence when we increase n max. So we expect that the optimal coupling will appear at n max equals infinity. So here, all curves fall on top of each other for mass of the bound state bigger than square root 2. So here, convergence is very good. So we believe this is indeed the optimal, the maximal cubic coupling that a quantum field theory can have. On this side, the bound is still growing, so convergence is a bit slower. We think that's related to the presence of singularities at the boundary of the disk. So this series, this truncated series, converges more slowly. But still, we have a finite answer the same way. So we can also maximize quartic couplings, but I think I don't have time to explain this. So let me skip to the last part of the talk, where I want to connect this S-matrix bootstrap that I was describing with the more better-known conformal bootstrap that we already had some talks in this conference. So the basic idea to do this connection is just to study quantum field theory in the de Sitter space or in hyperbolic space, and study correlation functions of boundary operators. Okay? So boundary operators, I just mean we can just take bulk local operators and then take their limit as we send the point to the boundary. And as you send the point to the boundary, that defines a boundary operator. So we can define boundary correlators by this limiting procedure, similar to what we do in ADS CFT, but this is different because there's no dynamical gravity, okay? So this ADS geometry is fixed, it's just quantum field theory on a fixed background. And then we can easily show that the isometry group of ADS acts on these boundary correlators like the conformal group, and we can also argue that these boundary operators defined this way have a convergent operator product expansion. And so, in fact, we have all the conditions to apply the conformal bootstrap techniques. Okay? So the message from this slide is that any quantum field theory in anti-de Sitter space provides you a solution to the conformal bootstrap equations. If you look at this subset of observables, which is these correlation functions of boundary operators. Okay? So once we have that, we can just now set up, So this is quantum field theory in ADS, but we wanted to connect with flat space. So to connect with flat space, we have to take the flat space limit of ADS. So that's very simple. So for example, the mass spectrum, we can just take ratios of dimensions, and when we take the limit of large dimensions, that gives you the ratio of masses. So that just follows from the fact that dimensions, if you want dimensions of these boundary operators, are energies of bulk states, and so in units of ADS, so they just scale like the mass of the particle times the radius of ADS. Okay? Similarly, we can analyze cubic couplings. So that just follows from analyzing what the local cubic coupling gives for the three-point function of boundary operators. So we just compute this Witten diagram, and we get a relation between the OP coefficient and the local cubic coupling. And you can also do it for scattering amplitudes related to Mellin amplitudes, but I don't have time to explain this formula. But there is a clean connection between quantum field theory in ADS and taking the flat space limit and extracting observables for flat space. So now we can just set up the standard numerical bootstrap. So we do the analog, so we consider a spectrum of dimensions where you have an operator dimension delta 1, then delta 2, and then 2 delta 1, and anything above that. So this is the OPE structure that we impose. Once we impose this OPE structure, we can now look at the 4-point function of the lightest operator, the lightest primary, and decompose it into conformal blocks. Okay, the conformal blocks. So here, here I'm doing the case where it's two-dimensional ADS. So the boundary theory lives just on a line. Okay, so this is conformal bootstrap in one dimension. So the conformal blocks is extremely simple. It's just this hypergeometric function. And now we can just maximize this OPE coefficient and imposing the crossing symmetry equations like we always do in the conformal bootstrap program. So here are the results for this bootstrap analysis. So if you plot the maximum value of this OPE coefficient as a function of delta 1, the dimension of the external operator, for some fixed ratio of delta 2 to delta 1, okay? Recall that the flat space limit, we want the ratio to be the ratios of masses. So let's say we fix it, just for example, then we will run over that value. Then you will see that depending on your computational power, so here in the conformal bootstrap, we have to truncate the crossing equation to some finite number of derivatives around the crossing symmetric point. So here you see, as you impose more constraints, the maximum value that you can attain is smaller, but you have more constraints. And so in fact, what you can do is extrapolate in this number of constraints to infinity. So if you plot all these points and extrapolate, you'll get this orange curve. And what's remarkable is that this orange curve in this log plot has a slope, has a linear slope, which exactly matches the formula that I showed you before relating OP coefficients to cubic couplings, okay? This exponential scaling just follows from computing a Witten diagram with a finite cubic coupling. You will get this scaling for the OP coefficient. And so then you can actually plot this picture where you extrapolate twice. So all these points extrapolating vertically are extrapolating in the number of derivatives of the conformal bootstrap. And then you extrapolate to large dimensions, so large delta 1, which is the flat space limit. So the yellow arrow is going to the flat space limit. And so you get these red dots here at the flat space limit. So here I already rescaled the OP coefficient to the cubic coupling using the formula I showed you before. And what you see is that all these red dots fall exactly in this black curve, which is what I showed you before, which is the analytic result for the maximal cubic coupling of the 2DS matrix. So the conclusion is that, at least in this case, for two-dimensional quantum field theory, this setup of studying quantum field theory in ADS and then using the conformal bootstrap to analyze these boundary correlators matches precisely what we get from the S-matrix bootstrap. Okay? Unfortunately, in higher dimensions, the numerics so far are not powerful enough so that we see the scaling predicted by the flat space limit. So you saw here we had to go up like to 200 derivatives of the crossing equation. And so in higher dimensions, that's just not possible because you have now two cross ratios and it's just too hard numerically. So I'm running out of time, so let me just finish with a long list of ideas for the future. So I will not comment on all of those because my time is running up. But let me just say that now we are actually working on this multiple amplitude bootstrap, where instead of just looking at a particular S-matrix element, we analyze all the S-matrix elements between the stable particles. So, well, we are starting with the case with 2, of course. And so in that case, you have a richer structure where the unitarity conditions become more complicated because you have sums of amplitudes that give you the total probability. And actually, that also relates with the second point, because now when you have different masses, in particular when you are scattering where your external particles are not the lightest particle in the theory, then you can have other singularities known as anomalous thresholds, which do not follow just from the mass spectrum of the theory. And okay, I'll leave this up. Thank you very much for your time.
Thank you very much for this beautiful and clear talk. Questions?
One small question. So in the conformal bootstrap, the truncation that is done leads to rigorous bounds. What about your case?
Sorry, the truncation that is done?
That is done in the conformal bootstrap. It leads to rigorous bounds. So
Yes.
for every n, so to speak, the bound that you get is rigorous.
Yes.
What about your case?
Good. This is a good point. So Zohar is emphasizing that the logic here is very different from the standard conformal bootstrap. So in the conformal bootstrap, we really get rigorous bounds because we truncate the number of constraints, but we never truncate the number of variables. We just leave we allow for all possible operators appearing in the spectrum with some gap conditions, but just that. So in that case, at any finite number of the truncation, I can even show you here the picture, right? So this bound was optimal. All theories live below this curve. Sorry, it was rigorous. Okay? Of course, you can improve it, but you know that there's no theory that lives above, for sure. What we do in the S matrix is we approach from below, right? I show you the curve going up because we increase the truncation number of variables. So what we do is we actually show that it's possible to find a solution of the constraint equations with that value of the cubic coupling. But we don't have a rigorous argument to say that's the optimal. We just have an argument based on numerics that we see that as we increase n max, it converges very well. But actually, there's also a different approach, complementary approach, which also works like in the conformal bootstrap. So you set up a functional that acts on the S matrix and gets you a bound exactly. So that's also something we are exploring. There is some work from the 70s from Lopez and Menessier that they worked out some idea along these lines, but they didn't have a like systematic numerical approach, so we are trying to update their construction to make a systematic numerical algorithm to get a rigorous bound also.
There's a question over there.
Sorry, I need to ask my question in at the most two parts. So first part is dumb. Are you considering gauge theories in this analysis?
If I'm constraining gauge theories?
Yeah.
So if you think that, for example, you have a confining gauge theory that you are scattering glue ball states, then all these S matrix properties apply, right, to scattering of singlet states, glue balls or mesons. Of course, I mean, I made specific assumptions of the spectrum. I was looking at scalar particles, so there are some generalizations that need to be done, but in principle it applies, yes.
Okay, so the other part is now I guess Shiraz and co have done a work a few years back about matter coupled to Chern-Simons theories. So in these theories, actually, if you consider scattering of matter particles, 2-to-2 scattering, then it's neither analytic or it does not satisfy the conventional channel crossing symmetry. It has a modified channel crossing symmetry. So that might affect this analysis. I mean, you have to consider the modification of channel crossing symmetry also into account to put the constraints.
Right. So in that case, what you're scattering are particles that actually carry charge under the Chern-Simons gauge field. So that's why the crossing equation gets modified, because, I mean, there's like some effective, some Wilson lines that make this process gauge invariant. So I think that's actually a very interesting case to study, to set up, I mean, update this or modify these bootstrap equations, because crossing symmetry is different, depends on these Wilson lines, and also these particles are not singlets, so you will have some isotopic degrees of freedom. You have to do some update our equations with this generalization. But yeah, it should be very interesting to see if we can find that theory as satisfying some or saturating some bound in this perspective. Yeah, that's a very good point. Yeah.
Thank you.
Ed?
So apart from making assumptions about the spectrum, you're also making optimistic assumptions about the analytic behavior of the scattering matrix, because you're assuming there are no anomalous thresholds.
Yes. So we are considering the case we studied now was scattering of the lightest particle. So in that case, there's no expectation of anomalous thresholds. I mean, there's no Landau diagram that you can draw that will...
I'm not sure that's true in general. There's no simple Landau diagram with an obvious interpretation. But I'm not sure it's true that in general, even for the lightest particle, the analytic properties of the S matrix are as simple as you're assuming.
Well, we should definitely discuss, but I think that to see these anomalous thresholds, for example, the mass has to be bigger than square root 2 than the lightest particle, so that you have some sufficiently, I mean, when you draw a Landau diagram, that it can be, that the Landau diagram does not live on a line, I think you need that. But okay, we should discuss. Maybe I'm missing something.
I'm not sure, I should say.
Okay, in view of time, let's thank the speaker again.